Hello, this is Mark Weitzman. Welcome to my YouTube channel, Theoretical Physics with Mark Weitzman. It's been a few months since I made a video. I've been quite busy and everything, but I wanted to make a blog video on something that I did finish today and that I've done over the last couple of weeks that I think might interest you on artificial intelligence and this deep seek stuff and reasoning models and theoretical physics. So let's get started. So a couple of weeks ago, I read this article. I read this article in the New York Times. When AI passes this test, look out. And, it's one of those usual AI articles, but then in the middle of it, it had this physics question. And I'll read it right now. A block is placed on a horizontal rail along which it can slide frictionlessly. It is attached to the end of a rigid massless rod of length r. A mass is attached at the other end. Both objects have weight w. The system is initially stationary with the mass directly above the block. The mass is given an infinitesimal push parallel to the rail. Assume the system is designed so that the rod can rotate through a full 360 degrees without interruption. When the rod is horizontal, it carries tension T1. When the rod is vertical again, with the mass directly below the block, it carries tension T2. Both of these quantities could be negative, which would indicate that the rod is in compression. What is the value of T1 minus T2 / W? Now, as I read that problem, at first I thought, well, it's reasonably complicated. It's definitely not a freshman physics problem in the sense that while some freshmen could solve it, and it doesn't require more than freshman's physics to solve, it's more on the level of a sophomore, junior level mechanics problem. In other words, it's a little difficult. You don't need to do the whole Lagrangian and Hamiltonian stuff, but you need to think carefully. So I decided to work out the solution, and after I worked on it, it didn't take me too long, but a few days later, and I intended to write it up and make a video on it just to show it, but a few days later, I got this email from, now I haven't done much with ChatGPT. I mean, I have them and I've used them on occasion, but I'm not an expert on any of these things or anything like that. So a couple of days ago, make it so you can read it. No, that's better. Keep it on that. Maybe you can read it, but basically it was an email from Poe, and at first I didn't even remember what Poe was, but then I Googled, and apparently it's some kind of thing from Quora, or Quora opens them. Quora is a service that has all these silly questions that people ask and other people answer. And so I saw Deep Seek R1 in this email, and I decided to try it. So when I tried it, I downloaded it and I installed it, and it had this Deep Seek, and I don't know why it has this puzzle in here first, but let me just get this. So I copied and pasted the New York Times description of the problem into Deep Seek, and then it started working on it, and it kept on, this is its output, and kept on going and going, and then kept saying, no, I'm wrong, starting again. It was like very difficult for a human to follow what it's doing, and it was doing a lot of things, wrong. But I was still impressed that it kept on going and going and going and going. And by the way, I should have said that this is a spoiler in this video. I'm going to solve this problem in this video, at least show it. and post the solution on my Piazza website. I have a PDF. I wrote a LaTeX. So it's 10 pages, very easy to follow. It's really only 5 pages, but it's got some imaging. And I really elaborated a lot, so it's not that long a solution. But meanwhile, DeepSeek kept on going and going. Then finally it came to the end where you can sort of get a summary of what it concluded, and it gave its answer as 5. And that wasn't my answer. So I was like a little perturbed that maybe I made a mistake or something like that. I wasn't sure. And so I Googled online about this problem trying to get the answer. Now, these problems, humanity's last exam, are designed where the solutions aren't supposed to be posted online, otherwise the AIs will find it. But I found this link on LinkedIn. There's this girl who has a PhD in physics, now working in data science. And she posted. And she posted not a full solution, just an outline of a solution. Here's the actual motion of the two masses. One is on a block. I'm going to watch it again. So you can sort of see that there's a block that slides on a horizontal rail, and then another mass that's at a fixed distance r from it by a rigid massless rod that sort of rotates around it. So it's a nice problem. And I even asked her if I could take images from this thing, which are in my paper. So here's my paper. I'm going to go through this very quickly because I'm going to post it and there's no reason for me to really elaborate on it. But I did this today. And actually I've been in you may notice that it looks like I'm falling asleep. I've been up 48 hours straight because news keeps on breaking, not just in the political world, which I follow very closely, but my 2 largest stock positions just got killed. Google came in with bad earnings and they lost 7%. That's my second biggest position. And Apple's been bouncing around like crazy all year long, and that's my biggest position. And then now all of a sudden China is striking back against the tariffs and investigating them, and they were down up to 6 points on the overnight markets. And I started to say, oh, what a bad day it's going to be after having a good day yesterday. Anyway, I decided to do physics to take away some of the pain of the market. And so I said I'm going to write up my solution. So I start with that same New York Times description of the problem. Then I post my solution. And so basically, this is the starting state of the problem. You have a block, this orange thing, that can only slide on this horizontal rail. So it's constrained, but it's frictionless. And the rod that connects the mass above it, this is a rigid massless rod. And this over here is the center of mass, this black thing. Oh, I see I got my mouse working in the image. I had trouble doing that. Now I figured it out. Hope it doesn't disappear. Now, what you're supposed to do is you're supposed to give an infinitesimal push to this mass over here. I'm going to call the mass, the blue thing, the mass, the orange thing, the block. Basically, you just have to pay attention to the mass because there's no external forces other than gravity which acts vertically. So there's no horizontal force, which means that the x component of momentum is conserved and it starts out at 0, and so it stays at 0. So the center of mass moves, but it only moves up and down. So here's an idea of how the mass on top of the block moves. Okay, I'm clicking on my image in the program. That's not going to work, obviously. So let me go back to here. I'm going to restart this. So you can see it moves up and down. And they want you to measure tensions at this point when the mass is at horizontal, when the rod is horizontal. They want you to measure it at this point and when it's vertical at this point. So you just need to calculate that. Okay, let me get back to my paper. So I show the images. This is where it starts. This is where you want to make one measurement of the tension. Basically, you need to figure out what the acceleration is. This curve, as I show very quickly, is an ellipse, so it's very easy to calculate what the radius of curvature of this is. And similarly down here. And then it returns here and eventually comes back. So I outline my approach that because the center of mass is stationary, if the mass, the one that moves, has coordinates x, y, then the block has coordinates minus x, 0. The block always is on the rail, so it has a vertical coordinate of 0. But its horizontal coordinate has to be opposite of the mass in order for the center of mass to remain at 0. So that's sort of the key to solving the problem. Now, vertical momentum isn't conserved because there's an external force, gravity, but energy is conserved. We're neglecting the tiny bit of energy that, like, the planet Earth acquires, because that's relative to the energy of the system. It's down by like m over me, so it's completely negligible. Now, I quickly get the equation of the orbit, which is just the two things are separated by distance r because the rod is rigid and has length r. So this is the equation, and it's an ellipse. You might remember this from high school, x squared over, well, I have it like y squared over a squared plus x squared over b squared equal 1. And so it's an ellipse that's oriented vertically instead of horizontally, and there's a semi-major axis r and a semi-minor axis r over 2. So then I just developed the conservation of energies. We start out where both masses are at rest, so there's no kinetic energy, but there is gravitational potential energy, mgr. And then in general, that's going to be equal to 1/2 m. This is the kinetic energy of the mass that moves around the ellipse. And then the second term is the kinetic energy, the y component of the kinetic energy of the mass that moves around the ellipse. And then we have the kinetic energy of the block, and because of the fact that the x-coordinate of the block is minus the x-coordinate of the mass, we have this expression, so it's the same thing, at least x-wise, but there is no kinetic energy for the y component of the block. And then we have mgy, which is the potential energy of the mass. So this simplifies to this equation. This is our equation for conservation of energy. Now, using this equation, it's very easy to get the velocities at the extreme points on the ellipse. The extreme points are, the top and bottom. These are the perihelion and aperihelion. And these are the minor vertices, which go through the center and are perpendicular to the major axis. This is the minor axis. So we're interested basically in this point here and this point here. Now, so looking at each point, like if you look at the point 0, r and you substitute in that equation, you can see we'll have a 2gr on both sides of the equation cancels. We have a sum of squares equals 0. So each must be equal to 0. So at the top, the x component of velocity of the mass is 0, and the y component of the velocity of the mass is 0. And this is the initial starting state, and when it comes back, this always has to hold anyway. Now, when we look at the left minor vertex, the equation becomes, there's no potential energy, so we just get this equation. We know that the tangent to the ellipse at the minor vertices are vertical, so the horizontal components are 0. So we have this equation here, dx dt equals 0 at that point. And then we have dy dt has to make up for the 2gr, and it's minus the square root of 2gr because it's going down. Then at the bottom, we can again use the equation. Now we have a potential energy of minus 2gr. The tangent is horizontal, so there's no vertical velocity. So we get the vertical velocity is 0, the horizontal velocity is the square root of 2gr. And so now at least we have the velocities, and that's sort of what we need to solve the problem. there's two ways of doing it. You could just use your basic physics intuition. You know, we have to get this osculating circle. We know that we can always approximate to a curve. We can get a circle at a point, the closest one that has touches it and has the same tangent, and then we calculate the centripetal acceleration of this circle. So there's two ways of doing it, and we can use known formulas, and I give a reference. Oops. I clicked on that. Okay. Sorry. Let me get back to where I was. Yeah. So it is okay. This was the reference that I wanted to look at. If I click on that, it will take you to a Wikipedia page on curvature of an ellipse. So I have references, and using those formulas, we know that letting a equal r and b equal r over 2 in these curvature formulas, we're going to get the radius of curvature at the top and bottom to be r over 4, and that makes sense because the curvature at the top and bottom is larger, which makes the radius of curvature, which is the inverse of curvature, smaller, and on the sides it's 2r. So using those values, and we use the usual acceleration equal v squared over r, freshman physics, and when we substitute the velocities and the radius of curvatures, we get that at the side point the acceleration is g plus or minus g. On the left side it's plus g, and the minus side it's minus g. And then when the mass is below the sliding box on that major vertex, we get the y component of acceleration is 8g. You can also do this, start with the equation for the ellipse and take time derivatives and get everything the same way and verify this. So if you're uncomfortable with that osculating circle, you can do it that way. Now the tension, it's tricky the way they define the signs and everything, and they should be more clear. Like at the starting position, what you have is you have gravity acting on the mass downward with force mg, the block pushing it up with force the opposite, upwards mg. And so basically I wrote that as t as positive when the rod is pushing the mass. When the rod is pulling the mass, as it is at the 2 points where we need to calculate the tension T1 and T2, the tension will be negative. So we already calculated the acceleration as g, and clearly on the side the rod is pulling the mass, so we're going to get the T1 is minus w. You can read my explanation a little bit more. With respect to T2, now we have a gravitational force acting downward. We know the acceleration is upwards of 8g, but we have a gravitational force acting downwards. So the tension actually has to be 9 mg or 9w, and the sign is again negative because it's pulling, not pushing. So the answer to the problem is T1 minus T2 over W, and it's minus W minus 9W W is equal to 8. Okay. Now DeepSeek doesn't get that. These are its, as I showed earlier, these are its final calculations. I don't want to go into everything that it does because it's hard to understand, but it does get this equation, W2 squared equal 8g over r is correct. That's the 8g that we got, but it gets the sign wrong. Instead of adding a g to the tension, it subtracts, and so it gets 7g. It says the tension is minus 7w, but that's wrong, unless I'm crazy. I don't know. The angular acceleration squared, this equation on the side is just it's off by a factor of 2. And I think it used the wrong radius of curvature here or something like that, but I'm not sure. So I get minus W for that. So it ends up getting 5. So I don't believe it. Anyway, what's interesting is if you look through this, on the one hand, it's impressive, but it's hard to, because it does do a lot of steps and it goes through a lot of reasoning. But it seems like it's found an analogous problem with a pendulum on a pendulum or something like that. It found like some various analogous problems on the internet to this problem, and it's trying to use ideas from those things to solve it. And it keeps on like going and then getting it wrong and then reversing itself, and so on and so forth. I'll just give you an example. Let's go back. It's constantly saying, this is getting too confused, meaning it's getting confused, and it's changing direction over and over and over again. That's why it's so long. So it's hard to make of it. I'm not an expert on artificial intelligence. From what I understand or what I was told, other AIs have different answers, and probably some have the correct ones. So I just, I don't know. But this was DeepSeek, and it was free. I was using it on Poe, and I have a certain amount of free points. So this kind of sort of tells you that, I may not be using nearly the most powerful one. Probably not if it's free. But it does show that advances are being made, and, what else can you say? So that's the end of this video. Thank you for watching. I'm not sure when I'll return to regular video uploading on group theory and quantum field theory. Eventually I'll get to it. I'm trying to sort of rebalance my investment portfolio so I can just take a few months off and not have to deal with a lot of the nonsense in the market. Things are like crazy out there because we have a crazy president, and then, and crazy things keep happening. So thank you for watching. I'll see you again, and once again, thank you for watching my channel. Bye-bye.